Hi guys, we're going to go over again how you deal with energy where you're talking about temperature changes versus phase transitions. And what you want to remember is as we heat or cool a compound, there are two different types of energy transitions that occur. When you're within one phase, say you're heating up some water, the temperature will increase or decrease, but you're going to stay liquid, solid, or gas. What's different is when a phase transition occurs, when a solid melts into a liquid or a liquid evaporates into a gas. These are different types of energy consuming or energy releasing processes, so we have to use different equations with each of them, and they each have different energy costs. The first equation is what we use when we're heating or cooling a phase, and this is the one that has the delta T, the temperature change component. The heat equals the mass of whatever the compound is times that compound's specific heat capacity times the temperature change. And this is because that specific heat capacity, that is the energy required to heat 1 gram of something by 1 degree Celsius. So you need to multiply that specific heat capacity by the grams of whatever it is, because 5 grams is going to consume more energy than 1 gram. And you also have to multiply it by the temperature difference, because raising something by 5 degrees is going to cost more than raising it by 1 degree. Now, this specific heat value depends on both the substance and the phase of the substance. Here we have a table showing the phases of water and their corresponding specific heat capacities. When water is frozen as ice, its heat capacity is 2.11 joules per gram degree Celsius. But when it's a liquid, it's 4.18 joules per gram degree Celsius. This is because the different ordering and the different densities of the molecules in each phase is going to affect how much heat is required to raise the temperature. The other equation that you may need to use is the one that describes phase transitions. This is the heat equals the moles times the molar heat of fusion or vaporization. And this one's going to depend on both the substance and the molar amount. And it's going to depend upon whether you're melting or freezing. So that's the heat of fusion you would want for that. Or if you're evaporating or condensing, then you want the heat of vaporization. Now this delta H is always in kilojoules per mole. Here we've got the heat of fusion and heat of vaporization values for two different substances. For water, its heat of fusion is about 6 kilojoules per mole, whereas its heat of vaporization is for about 41 kilojoules per mole. In acetone, the corresponding values are about 5.7 and 31.3. So you can see that going from water to acetone, we change what those heats are, and then going from a fusion process to a vaporization process also changes it. A rule of thumb is that it always takes a lot more energy to go from liquid to gas than it does solid to liquid. And this makes sense because the energy gap between liquid and gas phases is much, much larger than the gap between a solid and a liquid phase. Now we need to think about where we would use these equations. This is that same graph from your November 18th class notes, showing how the heat added changes the temperature of a sample of water. If we start at minus 10 degrees, that sample is frozen, it's ice. First, we need to warm that ice up to the melting point, and that's a process that is best described by the Q equals M Cp delta T, because we're doing a temperature change, we're not doing a phase change. Once we get to 0 degrees, however, all the energy we're putting into the system is consumed by converting the ice to water, which means that we need to use the phase transition. In this case, it's going to be the moles of the ice times the heat of fusion, because this is a transition between solid and liquid. Once all of the water is liquid, we're going to be able to change the temperature again. The water is going to heat up, which is another Q equals M Cp delta T process, except this time that specific heat is going to be for liquid water specifically. Once we've heated that all the way up to 100 degrees, then we've hit another phase transition. This means we need to use Q equals moles times, in this case, the heat of vaporization, because we're going between liquid and gas. This is going to consume a lot more heat than the melting phase, or the melting process. Once it's done, this steam can still absorb heat, and you're going to see a temperature increase again, and that means we need to pull out that Q equals mCp delta T, which is going to, again, have a different specific heat than the liquid water or the frozen water phases. If you wanted to calculate an energy change based on, going from, say, 10 degrees to 120 degrees, you would need to string together three terms. One that's heating the water from 10 to 100 degrees, which you would use this equation for. Then you would need to account for the evaporation process, which is what you would use this equation for. And then you would have to heat that vapor from 100 degrees to 120 degrees, which is where you would use this equation. And you just string together all the different terms you need. I'll see you guys on Monday for Hess's Law.